Now, speaker Vasyl Fedorchuk from Lviv. Title of presentation is on partial preliminary group classification of some class of 1 plus 3 dimensional Monge-Ampere equations, one-dimensional Galilean Lie algebras. Please.
Thank you. First of all, I am grateful to the organizers for the information about the conference and for the possibility to give me this talk. It is known that the solution of many problems concerning geometry, theoretical physics, namely astrophysics, differential equation, fluid dynamics, optimal mass transportation, one-dimensional gas dynamics, has reduced to investigation of classes of Monge-Ampere equation in the spaces of different dimensional and different types. At the present time, there are a lot of paper and books in which the classes of Monge-Ampere equation have been studied by different methods and different authors. First of all, I have mentioned the work of Ciceița, so-called surfaces of Ciceița, Pogorello, many-dimensional Minkowski problem, Xing-Tung Yao now still Nedis concerning string theory, cosmology, and other application of different type Monge-Ampere equation, which are defined in different spaces and different dimensional this space. I have present only some of the other and with consent studied classes of Monge-Ampere equation and its applications. As we see, there are others from different countries and different times in which classes of the Monge-Ampere equation have been studied by different methods. Let us consider the following class 1 plus 3-dimensional Monge-Ampere equations. As we see that class contains right-hand side depended on x0, x1, x2, and 3, which belong to the four-dimensional Minkowski space U and U0, U1, U2, U3, which denotes first-order derivatives from function u with respect to variable x0, x1, x2, and x3. F is an arbitrary real smooth functions. For the group classification of this class, we have used the classical Lie-Ovsyannikov approach. It is known that in 1881, Sophus Lie has published works concerning group classification of the linear partial differential equations. And if we say about partial differential equation, this work was the first on this topic. Next, in 1959, Ovsyannikov has been published your paper concerning group classification of the heat equation. And in the book of Ovsyannikov, 1982, we can find the method for the group classification of classes differential equation. Next work concerning connected with this topic is the work Fushchich and Serov, and the monography Fushchich, Stalin, and Serov. And many works concerning the group classification and the using symmetry property of the Monge-Ampere equation belongs to the Udrishte and Biwa. It is known the transformation from the Poincaré group P14 belongs to the group of equivalence of the class under investigation. Therefore, we can use the subgroup structure of these groups in order to perform the classification of the class under consideration. Proposition: the Lie algebra of the group P14 contains 21-dimensional non-conjugate subalgebras. Among these subalgebras, 12 subalgebras belongs to the so-called Galilean Lie subalgebra of the Lie algebra of the group P14. At the present time, we have performed partial preliminary group classification of the class under consideration using one-dimensional non-conjugate Galilean subalgebras of the Lie algebra of the Poincaré group P14. The subclasses obtained can be written as follows. Phi is arbitrary smooth function. J1, J2, J8 as a functional basis of the first-order differential invariants of one-dimensional non-conjugate subalgebras of the Lie algebra of the group Poincaré P14. Let us present an example which is connected with pure Galilean transformation generated by the operator P3. The J1 in this case equal x1, J2 equal x2, J3 equal x0 plus u, and j4 equal as follow in the equal has the form. It should be noted that J1, J2, J3, J4 didn't contain derivatives of the function u with respect to the variable x0, x2, and x3. But J4, J5, J6, J7, and J8 contains derivatives, first-order derivatives of the function u with respect to the independent variables x0, x1, x2, and x3. Therefore, they call first order differential invariants, since they contain derivative of the first order u0, u1, u2, u3. It should be noted that we can use the symmetry property of this subclass in order to investigate symmetry reduction of this class, and to do it, we can use usual scalar invariant J1, J2, J3, J4, and construct non-singular manifold which is invariants under Lie algebra generated by the operator P3. And this subclass has non-trivial symmetry property, and you can use this symmetry property in order to perform the symmetry reduction of this class to the class of the partial differential equations which contains three variables, three independent variables, instead of four independent variables as is in the class under investigation. Thank you for your attention.
Thank you very much. Is there any question, remark? No, again, thank you very much for speaking.